Hello, everybody, and welcome to today's webinar from the Energy Storage Technology Advancement Partnership Project. This webinar is being hosted by the Clean Energy States Alliance, and this is Maria Blaise Costello, and I'm welcoming you to today's event. Folks are still logging in, but we're going to get going because we have a lot of material to cover and only an hour. So what we're going to do is just start quickly with that housekeeping slide. And just to let you all know right off the bat, this webinar is being recorded and it will be posted up within 2 days of this broadcast on the Clean Energy States Alliance website, www.cesa.org/webinars. So you can find this webinar recording and all of our other webinar recordings there. So to begin with, all of you are on listen-only mode. All participants are muted, so we will not be able to hear you, but we hope that you will have questions as you watch this presentation today. If you do, please enter your questions into the question box that you'll see on your screen here. Type them in and then hit send. They'll be going to our host and he will review questions, and we'll get to as many as we can as time allows in the last 15 minutes or so of the webinar. So please don't wait till the end of the webinar to ask questions. Please submit them as they come to you. If this box on your screen is interfering with your ability to view the webinar presentation slides, you can hit this orange box with the white arrow. It will make the box disappear to the side. There'll be a little tab that's also orange. You click on it again and the webinar console box will reappear. So please feel free to do that. I'm going to turn this over now to Seth Mullendore. Seth is a project director at the Clean Energy Group and the Clean Energy States Alliance, and he'll be today's guest moderator. Todd Olinsky-Paul sends his regrets. He had another engagement that he had to attend to. So Seth, I'm going to let you take it from here. I don't know why these are advancing on their own, but you can go ahead, Seth, and start with CESA.
Sure thing. Thanks, Maria, and thanks to everyone for joining us today. It's going to be a lot of great information. So start off with a little introduction of Clean Energy States Alliance, or CESA. CESA is a national nonprofit coalition of public agencies and organizations that are working together to advance clean energy. CESA members, which are mostly state agencies, include many of the most innovative and influential public funders of clean energy initiatives in the country. CESA works closely with states as they develop clean energy policies, programs, and finance tools, and CESA also facilitates information sharing, provides technical assistance, coordinates multi-state collaborative projects, and communicates the positions and achievements of its members. Additionally, CESA develops reports, webinars like this one, and other informational resources on topics of interest to policymakers, clean energy stakeholders, industry, and academics. For more information, including the webinars, you can visit CESA's website at www.cesa.org. So today's webinar is going to be brought to you by a project in CESA that's called the Energy Storage Technology Advancement Partnership, which is managed by CESA. The ESTAP project, for short, is supported by the U.S. Department of Energy Office of Electricity and Sandia National Laboratories. The key activities of CESA include disseminating information to stakeholders, the listserv of over 5,000 members, and webinars like this one, conferences, information updates, and surveys. Also, the project facilitates public and private partnerships to jointly support federal and state energy storage demonstration projects, and you can see a map of project locations there on the right of the slide, so working all across the country. And ESTAP also supports state energy storage efforts with technical, policy, and program assistance. So we are lucky enough to have a couple of folks from Sandia National Laboratories today as our presenters. We're going to have Ricky Concepcion, who joined the Electric Power Systems Research Group at Sandia National Laboratories as a member of technical staff in 2014. He's conducted research in the areas of electric transmission systems and energy storage system valuation. He is the lead developer of QuEST, Sandia's open source software tool for energy storage valuation and related applications. We're going to hear a lot more about today. Other research interests include signal processing, optimization, and related fields. Prior to joining Sandia, he received a bachelor's degree in engineering physics and master's of engineering in electrical and computer engineering both from Cornell University. We are also joined by Nguyen, who is a senior member of the technical staff at Sandia. He's also a senior member of the Institute for Electrical and Electronics Engineers and an editor of the IEEE Transactions on Sustainable Energy. He received his bachelor's degree in power systems from Hanoi University of Science and Technology in Vietnam in 2007, and his PhD in electrical engineering from Missouri University of Science and Technology in 2014. Before joining Sandia in 2016, he worked as a postdoctoral research associate at the University of Washington. His research interests include energy storage, economics, microgrid modeling and analysis, and the integration of distributed resources into power grids. Okay, with that, I'm going to turn it over to Ricky and Tu to begin the presentation for today.
Great. Thank you, Seth, for the introductions, and thank you to the Clean Energy State Alliance for inviting us to present on this webinar. My name is Ricky Concepcion with Sandia National Labs, and I'm joined here with my colleague, Nguyen. And as the webinar description indicated, we'll be presenting about our software tool called QuEST. Okay. So here's a brief outline of the presentation portion of this webinar. First, I will give a brief overview of QuEST, what it is, its history, and why are we developing it, and why people should use it. I will then discuss briefly about how you can obtain and try out QuEST for yourself, although that's not the focus of today's presentation. Next, I will give an overview of each of the applications currently available in the QuEST application suite. So we market QuEST as an application suite because we would like to emphasize the diverse capabilities of QuEST using individual products and highlight QuEST's identity as a toolbox for energy storage valuation. Currently, the products we have released include QuEST VALUATION, QuEST Data Manager, and QuEST BTM. For this webinar, we decided
Ricky, sorry to interrupt. Could you speak slightly more directly into your microphone? Thank you.
Okay, no problem. For this webinar, we decided to showcase the newest application in QuEST, which is QuEST BTM, short for Behind the Meter. Tu will present about behind-the-meter energy storage systems and describe the valuation approach for those energy storage systems that QuEST BTM uses. Namely, we are looking at cost savings on electricity bills due to dynamic rates. Tu will then go through a case study that showcases a sample application of QuEST BTM in evaluating cost savings for a hotel operator using solar plus storage. This case study will simulate and illustrate using the QuEST software. Finally, I'll finish up and wrap up the presentation and describe our plans for the future and leave some time for questions from the webinar participants. So, QuEST is the energy storage valuation and analysis software tool developed out of the energy storage analytics team at Sandia. For almost a decade, the team has been conducting valuation studies for energy storage. The thrust leader of that team, Dr. Ray Byrne, has led efforts to evaluate the revenue potential of energy storage in each electricity market area in the United States. After developing a framework for conducting these studies, the team established a formulation that could be generalized into a tool. In the summer of 2017, the development team for what eventually became QuEST was founded. The goal of this effort was to create a graphical user interface, or GUI, to help users conduct the aforementioned valuation analysis, that is, to be able to evaluate the revenue potential of energy storage systems in different electricity market areas using a visual tool. Fast forward to September of last year, we publicly released the first version of QuEST, which included the electricity market-based valuation application, QuEST VALUATION, in addition to a data acquisition app, QuEST Data Manager, that we will discuss later. This year, we also added QuEST BTM and are currently on the version 1.2 series of updates. The software codebase is hosted on the GitHub platform, the public platform for open source software projects. So I've described why we developed QuEST, but the related question is why should anyone use it? So we developed QuEST for a wide range of audiences, for energy storage project stakeholders such as lenders or project developers. We want to create an accessible and easy to use tool to help them evaluate different prospective energy storage projects. For engineers and software developers, QuEST is our contribution to the broader open source software community. It's a showcase in GUI and application design and an example of optimization modeling using Pyomo, another member of Sandia's software ecosystem. As an open source software product, its code and machinery is entirely transparent, and the more intrepid users can go ahead and modify the code if they desire. Finally, QuEST is free to use. We distribute it under an open source distribution license and do not gate access to it. Furthermore, we welcome contributions to the project and always develop QuEST with users in mind first. So currently, QuEST includes 3 different applications. There's QuEST Data Manager, which is used to obtain data for use in other QuEST applications, such as electricity price data, load and photovoltaic power profiles, and utility rate structures. QuEST Valuation, as mentioned before, is aimed at performing valuation for energy storage systems, participating in ISO and RTO electricity markets through value stacking. QuEST BTM is for behind-the-meter energy storage systems, and currently it looks at estimating the cost savings for time of use and net energy metering customers. QuEST identity is based on and currently revolves around the application or GUI. This software tool is our bread and butter, so to speak, and we anticipate that most users want QuEST for this aspect. The application is developed to optimize the user experience and to make QuEST's analysis capabilities available in a streamlined experience. However, our goal for QuEST's future development is to also open up the so-called advanced usage of QuEST that we shall refer to as an API or a library part, and this is aimed at power users. This part of QuEST will provide unfettered access to the brains, models, and other code behind QuEST without the limitations of the canned experience from a graphical user interface. For example, you'll be able to queue up large batches of different optimization problems for sensitivity analysis. Or perhaps maybe you want to download all the electricity prices in the PJM market area since 2009. Such tasks like these will be possible by scripting in the Python language that QuEST is written in via this library. By exposing this API for QuEST, we'll be able to rapidly release new models and capabilities to users. We'll still develop new products in the QuEST application GUI, but we'll release new updates in advance through this API. So as I mentioned before, I'll briefly describe how you can obtain QuEST for yourself. So QuEST is maintained and hosted on a GitHub repository. The specific link to this may change. So I'll refer you to the DOE Energy Storage Systems website on the sandia.gov domain, specifically the tools section for the latest. QuEST is cross-platform and is usable on the Windows, Mac OS X, and Linux operating systems. Generally, it requires a few steps of installation, similar to compiling code from source. However, for Windows 10 users, we have a packaged executable version of QuEST. You simply download a zip file, extract it, and run an executable file. And installation through this method requires nothing except for an optimization solver, no Python or command line expertise required. Please refer to the README on our software repository for further details on this. Moving forward, I'm going to give a brief introduction to each of the applications currently in QuEST and provide some screenshots to help visualize what it feels like to use the software. This flowchart summarizes the general workflow of using QuEST. The first step is to decide what type of analysis that you would like to do based on the available application options. And as of now, there are 2 general categories. If you're interested in looking at value stacking in ISO and RTO electricity markets, QuEST Valuation is the app to use. If you instead want to look at behind-the-meter applications, QuEST BTM is for you. So once you've decided that, you need to grab the appropriate data for the analysis using QuEST Data Manager. For example, if you're using QuEST Valuation, you're going to need market data for the ISOs and RTOs that you're planning on looking at. Finally, once you've acquired the appropriate data, you can proceed to the app of your choice, set up your analysis using the wizards or other interfaces, and generate and view results. So first up, we have QuEST Valuation. This application generally seeks to answer the following question. Given an energy storage system in a certain electricity market with particular revenue streams available, how much revenue can the energy storage system generate? QuEST Valuation approaches this problem through a retrospective analysis. It uses a set of historical data, say the calendar year of 2018, and looks at 1 month at a time. In each month, the energy storage system has what we call perfect foresight of the prices, in that it knows in advance the prices for all value streams at each time step. We then formulate an optimization problem in which the system determines the optimal policy of bids or transactions in order to maximize its revenue over that month. As such, this procedure estimates an upper bound on revenue potential over that time period. In this screenshot, we have one of the sample reports showing how an energy storage system providing frequency regulation in addition to energy arbitrage would manage its state of energy. In QuEST Valuation, we provide a wizard to streamline the analysis setup. You can select which market area to participate in, which governs the problem formulation, data requirements, and value stream opportunities. You can then describe the parameters of the energy storage system. Our model is an energy flow model, which is parameterized by values such as energy capacity, power rating, and round-trip efficiency. There are opportunities to provide more advanced parameters through other interfaces. I should note that this particular model is technology agnostic because of the way this system is parameterized. The selection in this particular example serve as templates for those 4 pictured parameters based on projects from the Global Energy Storage Database. After completing your selections in the wizard and running the optimization, the wizard produces summary reports. It breaks down monthly revenue as computed, including splits by each value stream. Additionally, a pro forma summary document can be produced to memorialize the analysis that you had just performed. Next up, we have QuEST Data Manager. This application was born out of a need to help users acquire electricity market data that we had previously used in our market area studies, but could not distribute with the software. It has since expanded from there as QuEST data needs have grown. QuEST Data Manager makes use of publicly available sources such as ISO market data portals, APIs, and databases. In addition to market data posted by ISOs, you can acquire U.S. utility rate structures hosted and maintained by openei.org. From that same source, you can acquire hourly load profiles for commercial and residential buildings. Finally, you can also acquire photovoltaic power profiles using the popular PV Watts by NREL. As an example, this is the user interface for downloading market data from ISOs and RTOs. In particular, this one is for ISO New England. Since ISO New England requires registration and credentials to access their data API, you need to input that information into QuEST. You then select the range of months for which to download data, as well as which pricing nodes you want electricity prices for. QuEST Data Manager then automates the download process and stores it in a data bank for use in other applications. Going through a few more examples, you can search for utility rates. In this example, we're looking up Pacific Gas and Electric in order to get the correct rate structure for the case study later on in this webinar. The rate structure data includes all of the relevant information, such as time of use rates and schedules for both energy and demand, flat demand charges, if applicable, and so on. These also may be modified as needed by the user. Hourly load profiles for commercial and residential buildings may also be obtained. This data is based on an effort to simulate building load based on typical meteorological years. You can search by state and city, which determines the climate used for the simulation. Commercial buildings are differentiated by type, such as a quick service restaurant or office building, and residential buildings are differentiated by the level of load. Lastly, we have the interface for acquiring PV power profile data. You can specify the coordinates of the panel location and other parameters such as nameplate capacity, panel and mount type, and efficiency. This will return 1 year of simulated AC power output using the PV Watts API. Finally, I'll briefly introduce the latest application to join QuEST called QuEST BTM. Short for behind the meter, QuEST BTM aims to cover different tools for behind the meter applications of energy storage. Currently, it includes a tool for estimating the cost savings using energy storage for time of use and net energy metering customers. It incorporates specific utility rate structures like we discussed previously from QuEST Data Manager, and additionally uses load profile data and optionally co-located PV power profile data. Similar to QuEST valuation, it looks at 1 month at a time for 1 year's worth of data. For each month, a problem is formulated so that the energy storage system minimizes its total costs over that month. Like with QuEST valuation, QuEST BTM also provides a wizard to step you through the analysis setup. You will select a rate structure from your data bank. And here we have a summary describing the selected rate structure, including time of use rates and schedule for energy and demand. Likewise, you will provide parameter values for the energy storage system, such as energy capacity and power rating. Once you've completed the wizard and the optimization is performed, QuEST BTM also provides summary reports at the conclusion. These reports are focused on comparing the impact of adding an energy storage system. In this example, we're comparing the total bill, the sum of all charges with and without energy storage. And in this example, we're looking at how the peak demand each month was reduced with the addition of energy storage. For rate structures with time of use demand charges, we typically see the bulk of cost savings accrued through demand charge reduction like this. So the remainder of this presentation focuses on behind the meter energy storage and QuEST BTM. So I'll now hand control over to my colleague Tu, who will discuss behind the meter energy storage and walk you through the case study using QuEST BTM.
Thank you, Ricky. Next, I will give you an overview of the utility rate structure in the US and how behind the meter can help the customers lower their bills. As you may know, the terms front of meter and behind the meter are often used to specify the system location. Behind the meter refers to the systems that are located at customer sites, for example, homes, commercial, industrial facilities. Behind the meter systems are usually owned by the customers and intended for customer use, while front of the meter systems are owned by the utilities and intended for grid services. Whether or not can behind the meter energy storage help reduce customers' electricity bill depends on the utility rate structures, or in other words, it depends on how the utilities charge the customers for their electricity usage. Before talking about the utility rate structures in details, I would like to introduce some important terms here. The first term is energy charge. It is a charge to the customers for the energy in kilowatt hour consumed in a billing period. This charge is applied to all customers, including residential, commercial, and industrial. The second term is demand charge. This is the charge to the customers for their peak power uh, demand in kilowatt. This charge is often applied to large commercial and industrial customers. Besides energy and demand charges, there are also other charges that are independent of consumption, such as meter fee and some other basic customer fees. The first rate structure I'd like to talk about today is a fixed rate, or often called a tier rate. It is a rate structure where a constant price is applied to each tier of energy consumption. It should be noted that flat rate is also a special case of tier rate where only one tier is specified. The figure in this slide shows an example of PG&E's tier rate for California customers, in which the higher prices are applied to the higher tier. And of course, different utilities have different prices and tier specifications. The fixed rate is the most common and probably the oldest rate structure used by the utilities in the US. The main advantage of this rate structure lies in its simplicity. However, it does not reflect the time-dependent characteristic of electricity price. In opposite to the fixed rate are the dynamic rate structures, where energy and demand prices are time-dependent. The utilities' motivation for dynamic rate include increasing customer satisfaction with options to reduce energy bill, increase load growth, reducing total peak demand by load shifting, and complying with regulatory mandate. The most common dynamic rate is time of use pricing. In time of use pricings, energy and demand prices are set in advance for different time periods. Time schedules for time of use often classifies hours of a day as peak, part peak, and off-peak hours, day of a week as weekdays, weekend, and holidays, and month of a year as summer and winter months. This picture shows an example of a time of use schedule from Southern California Edison, in which the off-peak hours are from 10 p.m. to 8 a.m. every day. The peak hours are from 2 p.m. to 8 p.m. every weekday, and all other hours are specified as part peak hours. You can see that the energy price varies during the day, and there are different price settings for weekends and weekdays, for summer months and winter months. Besides time of use, there are also other dynamic pricing options, including real-time pricings, variable peak pricings, critical peak pricing, critical peak rebate. Variable peak pricings is very similar to time of use pricing, except that the peak period prices change daily to reflect the system conditions and costs. The critical peak pricings, on the other hand, is similar to the flat rate, except that the price may increase dramatically when a critical event occurs. Critical peak rebate is also similar to flat rate, except that the customer are paid for reducing the consumption during critical events. Other than the above rate structures, the utilities also introduce net metering programs. As more and more customers own rooftop or on-site PV systems, these programs allow the customers who own renewable energy systems to export their excess energy to the grid. The net energy exported to the grid will be used to offset the customer consumption, and at the end of the true-up period, the customers will be charged or credited for their energy usage or surplus. Generally speaking, the longer true-up periods are more beneficial to the customers because the surplus energy in some months, instead of being sold to the utilities at wholesale price, can be used to offset the usage of some other months. However, that might not be true if the customer's surplus energy are paid at the real retail electricity price. To benefit from dynamic rate structures, the customers must be able to change their loads in a manner that lowers their bills without interrupting their operations. Commercial and industrial customers, or sacrificing their conveniences for residential customers. Therefore, behind-the-meter energy storage can be used to provide the needed flexibility for the customers. For example, net metering customers can increase their savings by storing the excess renewable energy when the load is low and use that energy later when the load is high. Time of use customers can benefit by charging their batteries during off-peak and then charging them during peak hours. Time of use customers can also reduce their peak demand by discharging during peak hours. Given the limitations in energy storage capacity and efficiency, the economic gains are highly dependent on the storage size and operation. To justify the deployments of behind-the-meter energy storage, it is essential to optimize these factors to maximize the overall benefits for the customers. This is an optimization in which the objective is to minimize the total energy charge, demand charge, and net metering charge, considering physical limits of energy storage device and the inverter. The decision variables of this problem are the charge and discharge power of the storage device at each hour. We have incorporated the above optimization framework into QueST BTM to help the time of use and net metering customers evaluate how much they can save on their bills by using energy storage. Now I will give you a case study that step-by-step walk you through QueST BTM application. In this case study, we consider a large hotel with solar and storage. First, we will need to use QueST Data Manager to get the data that we need. For this analysis, we will need utility rate structure, load profile, and PV power profile. Let's assume our hotel is a time of use customer, a PG&E following rate structure E19, medium general demand time of use. The data manager gives us different search options to find this rate structure, including search by utility name, search by zip code, and search by state. For example, in this case study, we search by the utility name. Once we find the utility, we can use a filter to narrow down the search results to find our rate structure. Please note that we will need an API key for this tool and the PV profile downloader. There's a help prompt to get you started with that short process. Once we find the rate structure we want, we continue to verify all the time schedules and prices. This screen shows you the time of use energy prices on the left, corresponding to the time of use energy schedules on the right. For example, the red blocks here in the time schedule, which are the peak hours from noon to 6 p.m. every weekdays in the summer months, are corresponding to price tag number 4 at 16 cents a kilowatt hour. If we find any differences in the downloaded data compared to the real data, this screen also allows us to modify both prices and time schedule. Now we continue to verify the demand rate structure. In this case, both time of use demand and flat demand are applied. Again, we can modify the data if needed. Now we can finish up the rate structure setup by selecting the net metering rate structure and save the rate data for later use. Next, we will need to obtain the load profile for our load. Since it's a large hotel, we will select commercial load profile. We will need to select the location and the type of the load we want and save the data for later use. Finally, we will need to download the PV power profile. In order to do that, we will need to enter the lat-long information, the PV system specifications, and also save the data. Once we are done with all the data setup, we will start using QuEST BTM for the analysis. First, we will use time of use cost saving wizard to set up the analysis. Processing through the wizard, we select the data that had just downloaded, including the rate structure, the load profile, and the PV profile. Now we can enter the energy storage system parameters. In this case studies, our energy storage system is 400 kilowatt hour and 100 kilowatt, so we can enter that in. Once everything's set up, we will click next to initiate the model building and solution process. In the background, the specified data is being loaded and the optimization models are being constructed and the models are being solved. After a brief wait, a prompt will notify you that the computation is complete. We can now view the wizard report of results and view several summary graphics. Based on the calculation, the addition of energy storage reduced annual charges by about $36,000. This was mostly due to demand charge reduction. Specifically, the peak demand each month was reduced by about 100 kilowatt in this case. Now we can also create a summary report that includes all the formulation details and the results. And we can finish our case studies here. And we can also always retry the wizard for different energy storage system parameters, or we can try different PV or load profiles, rate structure, and so on. Is this energy storage system worth it? It will depend on financial of acquiring and operating it. But we have an estimate on its performance value potential. So here are our related papers on energy storage evaluation for different applications. Please check them out if you are interested in detailed formulation and optimization frameworks. And with that, I will hand the control to Ricky to wrap up our presentation.
All right, great. Thank you, Tu. So future plans for QuEST. We plan on keeping development of QuEST going into the future. And while we are currently settling on a development roadmap for this coming year, Here's a list of some of the few ideas that we brainstormed recently. We have plans for creating a tool for helping states or utilities meet their renewable portfolio goals with integrated resource planning. We'd also like to incorporate estimating costs of using or acquiring energy storage and integrating that into the optimization process. Resiliency and how energy storage can help in resiliency is always a hot topic. And we'd also like to further expand the range of value streams used in QuEST valuation. As mentioned before, we're also planning on exposing the API and library aspect of QuEST, continuing community outreach through webinars such as this one, and gathering feedback and requests from both users and interested users. Finally, I'd like to acknowledge the funding, support, and guidance from Dr. Imre Juk, the Program Manager for the U.S. Department of Energy Office of Electricity Energy Storage Program. Feel free to visit our website and software repository and/or drop us a line if you have any questions or comments after this webinar. And with that, I'll turn it over to Seth.
Great. Thank you very much, Ricky and Tu. That was a lot of great information in there. And thanks to everybody that has been submitting questions. We have a lot of them. So we're going to get to the ones that we can right now. I'm going to kind of ask them as they came in, though we may jump around a little bit just because we've got a lot of questions and not a ton of time. I believe we do have the availability to stay on the line a little bit past the hour. For those of you that can keep on and join us, we may do that. For those that can't, the webinar recording will be available and the slides will be available. We'll send around a link in the next couple of days so that you all can log in and see if your questions got answered afterwards. So to start things off, there's a question about the interoperability of QuEST with other software programs like Helioscope or Energy Toolbase. Is there any compatibility between this and other energy analysis optimization programs?
So currently, there's no direct interoperability with other energy storage or energy software. Our plans in the near future is to integrate with the immediate Sandia ecosystem in terms of power system software, such as unit commitment and other related softwares. But in terms of direct interoperability, there's not that capability yet. I think the closest to that would be being able to export your results from QuEST and import them to other tools if that works out.
Mm-hmm. Great. So the data that in the data manager, how often is that information updated?
Since the QuEST Data Manager taps into live sources on the web, it's up to each individual source. So in terms of ISOs and RTOs, I think they have a regulatory requirement to post their data as soon as possible. So usually you'll be able to get data within the same day or yesterday. In terms of like OpenEI for utility rate structures and things like that, it's up to the maintainers of that database. And for load profiles, that they're based on a study from a couple years back, so those aren't particularly dynamically updated.
Great. So a couple of related questions to that. I know people had asked where the tariff information came from. So OpenEI, is there planned ability to be able to allow users to enter their own rate structures in case they're not in OpenEI or if they're playing around with custom rate structures?
So in terms of custom data, that capability is currently available, just not too well documented. We've left a note on how to do that in the README section of the repository. But for the future, we're planning on, since that's come up a lot, we're planning on creating a user interface for entering in your own custom data, such as your own load profiles, own PV power profiles, and things of that nature.
Great. Yeah, a lot of questions came in on that. That's great that you're already starting that process.
For the tariff structure right now, you can always download one closest rate structure, and then you can modify the information such as the prices and the schedules if you need it.
Okay, so you do have that ability to adjust the rate structures that are in there.
Yeah.
Excellent. So a couple of questions came in asking about does the model account for battery expected life or degradation of the battery system, assuming tapping into different different operational needs of the batteries for different valuation streams. Does the degradation factored into that analysis?
That's the questions that we hear a lot, and currently we don't have that capability yet. We don't have any degradation costs in our model, but in the future we'll plan to include that cost into our models.
Great.
And that'll be technology specific. You'll have to limit it to say like lithium-ion batteries if you have a model for that, and that'll deviate a little bit from how we model the energy storage system currently. But yes, as you mentioned, that's in our plans for this year.
Excellent, great. So for the front of the meter case, does QuEST optimize at all for value streams? Yes, assuming that there is limited ability for the battery to respond to all potential values, or does that need to be defined by the user?
So currently for front of meter stuff, we focus on frequency regulation and energy arbitrage. And since the regulation signal is not typically data that's available, we have parameters that estimate the ability of an energy storage system to respond to a regulation signal. And we parameterize that through certain fractional parameters.
Okay. Is there any ability to combine value streams from the front of the meter and behind the meter? Say, if behind the meter battery were large enough to participate in front of the meter, is there a way to do both of those analyses at once, or do you have to kind of do them independently and then layer them on top of each other?
Well, I would say currently we don't have that capability, but we building the API. We will provide the interface for the researchers can log in or can access our library of functions, and the researcher or anyone can use those library to do any analysis that they want.
Great. There's a question here, and I think this would be a more, is this on the horizon? Is there ability to reverse engineer getting the optimal battery size for the behind the meter based on, or front of the meter based on value targets?
So right now with the value evaluation, you can estimate the revenue that the system can generate. From that number, you can basically calculate the zero NPV point, from which you can actually calculate the maximum amount of money per kilowatt hour that you should pay in order to meet some payback time, some expected payback time. For example, if you earn $1 million a year, then let's say you want to get it paid back by 10 years, then you cannot pay more than some amount of money for your system. That's the way that we can reverse engineer. But usually if you have the information about the cost of the system, you can basically enter the revenue in that and then calculate the NPV or any kind of cash flow you want.
Mm-hmm. Mm-hmm. And is that functionality built into it now to do the net present value or return on investment, or is that a separate calculation step?
Well, that's not the focus of our tool. It could be calculate separately.
Yep.
Yeah, and since that comes up pretty often, while we've in the past and currently shied away from the financial calculations and things of that nature, since it's been requested a lot, we'd be open to adding some rudimentary calculations of that nature.
Great. Okay. So we actually have gone through a number of them. I'm just trying to read through some of the new questions that have come up. There was actually a question about the program SAM. Somebody noted that the interface reminds them a lot of SAM and wondered if there is any of the same engine driving QuEST that also drives SAM. If you're familiar with what's behind the scenes on that as well.
So we are aware of SAM, which is a system advisor model, I believe, by NREL. I don't think any of us have used it, so I guess it's a compliment that it reminds people of SAM. But since it's been in development and developed by NREL, we do not use any sort of the same engine behind them. So as I talked about before, we developed this from scratch about 2 years ago.
Great. Question on
more SAM is more focused on the financial project, and it is for a renewable energy system in general. And our tool is more focused on energy storage. It's more energy storage centric.
Yeah, actually, there's a related question to that. In the results for the behind the meter example that you showed, in the demand savings and the savings, does that take into account demand savings that would be achieved by a combination of the PV system and the storage, or is that just looking at what the energy storage system would be able to deliver to the site?
So in terms of the difference that we were showcasing, in this case study, we were looking at solar plus storage for the commercial operator. And in both scenarios, with and without energy storage, the PV is included. So in that sense, we're just optimizing with the addition of energy storage, assuming that the PV is already a given.
Okay, so just to make sure I've got that, so any savings that would be achieved from the PV system are already assumed to be included, and it's just the additional value that the energy storage system provides that is shown. Is that correct?
Yeah, that's correct. The only variable is the existence of the energy storage system. Great.
Those are interesting questions. So for the behind the meter, there's a question about if charging can be constrained to solar only, in order to be able to capture the full investment tax credit eligibility, which I guess could impact the performance of the system to be able to meet some of the peaks if it's not being recharged. Is that something that's in the system or something that maybe on the horizon you guys are thinking about?
Yeah, that is right. But for now, we don't have that constraint in our system. The battery is free to charge from any system, from PV or from the grid. But if you want to capture that ITC benefit, that sometimes you need to charge the battery purely from the PV, or like 70% from the PV, then yes, it will impact the revenue stream. But on the other hand, you will gain some benefit from ITC. So currently we don't have that, but later on we can add simply that a simple constraint that we can add.
Great. A question about how the equipment specifications that you use for the battery, how is that information collected and maintained for the tool?
So currently we sort of abstract away the equipment specifics of the energy storage system. So most of our modeling involves looking at the energy storage system as a energy flow model and isn't based on or modeled after particular equipment or technologies in general. So that's not currently a feature of QuEST.
Mm-hmm. So another interesting question. This is rather specific to one program. So there's a question about Massachusetts has a solar incentive program called SMART that has an adder for energy storage. So there's a kilowatt hour adder to the PV output. Is that something that could be modeled through QuEST? It's pretty specific to this one program, but I don't know if there would be some way to be able to simulate that through QuEST.
So I guess generally speaking, the challenges of developing a tool is that it has to be general enough to cover a lot of cases, but the curse of that is that a lot of or most scenarios are very specific to their instances, and so we don't currently have tools like that to model specific, like location-specific structures. But I'll say that the Sandia Energy Storage Analytics team has done a lot of site-specific analysis like that. Like, for example, we've done analysis based on New York's idiosyncrasies. And with the addition of an API or library type side of QuEST, we'll be able to produce more specific models like that. So there's a lot of that in the backlog of the team's capabilities, but hopefully if we come across studies like that, we'll be able to generate it into a tool that's usable by those specific audiences.
Great. I have a pretty related question to that, and this is actually, again, a Massachusetts program, but has been considered in other places is value stream like the Clean Peak standard, which would be probably more like the front of the meter valuation that you're doing. Are you looking at those types of programs, and assuming that would become more popular in other areas? Do you see the ability to be able to add new value streams fairly easily to the tool as they arise?
So in terms of adding new value streams, we're always keeping an eye out for changes to market structures, regulatory changes from FERC and things like that. And as I mentioned before, we're going to keep updating and trying to add new value streams to each formulation. To date, a lot of the legwork and modeling and analysis that has gone into QuEST was based on prior or related studies that our program as a whole has conducted that was then turned into a tool. But if we conduct analysis for, say, Massachusetts, then it'll most likely be able to make it into an update for QuEST if it makes sense to do so.
Mm-hmm. Great. So one more specific question here, and we actually did a great job getting through these. There's still a couple more coming in, but we're at the hour almost here. So this is specific to rate tariffs that are structured as a demand ratchet. For folks that don't know, demand ratchets are often rates that it will be based on your maximum demand over the past, say, 12-month period or the previous 3 months. They can be structured in different ways, but they're not always set month to month. Does QuEST able to take account of a complex structure like a demand ratchet?
So currently we're looking at monthly demand charge, but mathematically, in terms of formulation, we have a more general framework that can take into account that kind of demand ratchets. So later on, if we release the API, the user might be able to use that API to input any kind of period that they want instead of monthly.
Great. Okay, well, with that, I see we're at 3 o'clock by my clock here, or at the end of the hour for the webinar. I'm East Coast time here. So thank you very much, Ricky and Tiu. This has been really excellent, and I do think we actually got to most of the questions that people were asking. Several people asked similar questions, so that was fantastic. So with that, again, yes, thank you guys very much for all the great information about this great tool that you've developed. And thank you to everyone who joined us today. I'm going to turn it back over to Maria for a couple of closing thoughts.
Thank you, Seth, and thanks again to our guest speakers. I just want to alert the audience that we have an upcoming webinar on November 19th on Energy Storage 101. This is a series that we're doing. This is part 3 on energy storage applications and economics. We will have Ray Byrne of Sandia be our guest speaker at this event, so this should be also a very interesting webinar for all of you. And eventually you will get a notice of a December 5th webinar where we're featuring the Sacramento Municipal Utility District's carbon reduction strategies. So 2 upcoming webinars that will be of interest. So do look out in your email for new announcements for those. So thanks again, everyone. This is going to be recorded, and you should all get a link within a couple of days that will point you to both the slides and the webinar. So thanks again for joining us, and we look forward to having you on a future presentation. Take care.